I'm going to be talking more about how we can use different machine learning methods for solving problems in material science, specifically with a focus on energy storage and development of novel batteries. And so this is a huge problem because by 2030, around 45% of our power generated will be from renewables. But in order to be able to do that, we need to almost 20 times the amount of energy storage capacity that we have today. So this is a big problem that a lot of leaders have been talking about. One example being Bill Gates. If you think about the cost of renewables, they've significantly gone down compared to non-renewable sources. But the main reason we're not able to reliably use solar or wind is because the sun isn't always shining and the wind isn't always blowing. And so the real root cause here is being able to develop novel energy storage technologies that can help power sources when the sun isn't shining or the wind isn't blowing. And this will be really important for grid storage, whether it be home applications, grid storage, or electric vehicles. And so the real opportunity is discovering novel materials that can help us develop the next generation of long duration energy storage methods, but also develop higher energy density batteries that we can then use to power applications in grid storage or electric vehicles. And if you really break it down to the fundamental question that you're thinking about on the science side, it's really just what are the properties of a given set of atoms? And you're trying to figure out what these properties are then to be able to develop and synthesize new materials that will be effective for the application that you're trying to develop. And so material science today is a very, very manual and slow process. Oftentimes you're in a lab, you're doing tons of experiments, spending months, sometimes even years trying to find a right material for your application. And let's say you do find a material that you want to be able to commercialize and put into industry. That process alone can take 20 years and billions of dollars in funding. There is some research being done in computational methods to help accelerate material science. Oftentimes this is using physics simulations or DFTs for prediction. So you would start out with some initial crystal structure that you're trying to validate, and then you would do DFT structural relaxation on it, and then you just use DFT to do property prediction. But if any of you have worked with DFTs, you know how long it can take, and they're not the most efficient process today. And so a lot of what machine learning is trying to do is replacing that last part and using it for property prediction. There is also some work being done for DFT structural relaxation and replacing the whole pipeline with more data-driven approaches. But I won't be talking too much about that in my presentation today, just because that's a whole other area of research, but I'm happy to talk about that if you're interested. Because that can also be a bottleneck, right? Especially for structural-based models where the input you're taking into your machine learning models are these structural relaxations. That still takes a lot of time. Running those DFT structural relaxation before you can run your ML models can still take a lot of time. So that ends up being a bottleneck and really speeding up the entire process. So the core problem here is really just that you have a very large search space. So the naive kind of estimate here is around 10 to the power of 7. Those are the kind of that's the search space that you're really looking at when you're trying to develop a new material. And one example we can look at is the Materials Project, which is an open source data set full of different crystals. And so here you can see, relatively, let's say energy is relative to kind of all these other predictions and properties, you have a lot more data or number of crystals that you've collected. But if you look at things like phonons, you don't have as much number of crystals and data that you've collected for that. But after a certain threshold, you can start to do reasonable ML on top of these using the data that you have. And then a threshold above that, you can start to do more deep learning methods as well. But really the challenge here is that we don't have enough data. And as we all know, to be able to run really good predictions, we need a lot of data. And so the goal is to be able to use ML to help us predict everything else in place of that. So this is kind of the general pipeline for machine learning and material science. You often start out by identifying a target and a problem that you're trying to solve. This is similar to any other problem that you'd be looking at. And then you have data collection, which I'd say is the really, really big piece. And there's two ways to do this. There are some open source data sets that you can use, things like the Materials Project, which I mentioned earlier, or you can also use existing packages like PyMatGem, which help you collect your own data sets. And once you've collected this data, I'd say the really big piece is thinking about model choice and problem featureization. So once you have your data, it's thinking about how do you actually represent the materials that you want in a way that would be most effective based on the predictions that you're trying to make. So I'll be spending a lot of my presentation talking about this because I do think that's a really big piece of the puzzle. Then you have training, which obviously I think there's a lot more kind of resources out there on training and how that's done. So I won't be touching on that too much, but you spend time training your model, and then at the end, you think about the application, which is another big piece that I do want to talk about, because once you do make these materials and you do have these predictions, the big question is, how useful is this? Are we making predictions that we can then use to make real materials in the real world? And so that's a big piece that I think we're starting to think about more in material science and just AI and science in general. One thing that I do want to highlight is you don't necessarily want to have a purely data-driven approach, right? You don't want to just throw data at your model and then hope that it's able to make a bunch of predictions, and you can use some of those predictions to then synthesize a new material. The big piece here is really you want to make sure your materials still obey chemistry and physics law. So these are things that are very well known, things like thermodynamics or locality, the fact that atoms that are closer by will have stronger interactions than atoms that are further away. Things like symmetry, so you're looking at translation, rotation, reflection, and permutation of identical atoms as well. So the trend that we're really seeing here, instead of having a purely data-driven approach, is actually spending time integrating more physics and chemistry into our machine learning models. And I think this hybrid approach will be really important when we're thinking about building models that have more physics intuition built into them. So there's a lot of existing kind of crystal graph neural networks that some of you might have heard of or come across, things like CGCNN, you have MagNet, MAL-CLR, which uses contrastive learning, and then you have GAT-GNN. So there's a lot of existing kind of models out there, and most of them do follow this like graph-based structure because it's a really great way for representing molecules and crystals. For today's presentation, I'll be talking mainly about MagNet because I think it's a good example of kind of generally how these problems are formulated and represented. But obviously a lot of these models have variations and are benchmarked against each other, perform better on certain properties than others. So generally how you formulate graph and molecules in this structure is you have your nodes representing atoms, and then your edges represent the bonds between those atoms. And the way you represent this as an input into your model is off each edge and each node will be represented as a vector of numbers. So you can see here, each atom has a vector associated with it, each edge has a vector, and then what you're doing is within each atom and each edge, you're also embedding in certain things. So these can be things like for atoms, you'd embed the atomic number. For bonds, you can embed things like the distance between the atoms. And then we also have this global state vector. And this global state vector is really just representing overall properties for the material or the system that you're trying to represent. So these can be things like temperature, pressure, or entropy in your system. And how this model really works is it's just a sequence of updates that are happening. So you have a bond update, which what this is really doing is it's taking information from atoms that are connected to this bond. It's passing this information alongside the global state information to then be able to update the bond vector using a bond update function that you have. So really this can be thought of as like information flow. You want to continuously be updating your edges based on the atoms that it's connected to and the types of bonds that they have. Then you have your atom update, which is very similar, right? You're updating each atom from information from the bonds that are connected to it, and then also using information from the global state and flowing that into the atoms. And finally, you have your state update. So this is really updating state information from all of the bonds and all of the atoms that are connected to those bonds. And you might be wondering, like, how do you really find that update function? Because if in all of the bond, atom, and state functions updates, you have this update function. And that's usually just done through like a feed-forward neural network. So it's just using the universal approximation theorem to be able to find that and then use that to update all your values. The overall architecture of this model, so what I described would really just be like one part of this network. And the key benefit for MagNet is really that it's very modular. So you're able to stack multiple layers together to define how much complexity you really want based on what you're trying to represent. So an example of this would be, let's say you want atoms to be able to see other atoms that are very far away. In that case, maybe you'd actually stack more blocks together to be able to represent this. Now I want to talk about a core problem in material science, and I touched on this a little bit and how important data really is, but it ends up being a huge bottleneck when you're thinking about applicability and are we really making predictions that are useful in the real world. And so here's an example of band gap material. So that's just one thing that you'd be predicting for a material. And you have different DFT functionals that you're usually looking at that you can use to be able to do these predictions. So these are things like PBE, you have HSE, or experimental data. Now experimental data is the most valuable, right? Because this is like ground truth value that these are ground truth values you can use to know if your prediction is useful and matches up. But that's often also the most expensive to collect. So we have the least amount of experimental data. And similarly, we don't have as much data for HSE just because it's more valuable, but it's also very scarce and we're not able to collect as much of it. Comparatively, you have functionals like PBE, which are much cheaper to collect, so you have a lot more data for PBE. And so if you think about your model and your prediction, you're using a lot of PEE data to be able to make your prediction. And so if you think, in a sense, your predictions end up actually being very inaccurate because you're making predictions on inaccurate data. And so the question here is, how do we start to integrate more of those high valuable functionals and data sources into our models rather than having to train individual models on each of these different functionals? And especially if you have limited amounts of data for some of these functionals, your prediction will not be as accurate compared to when you're using PBE, which you have a lot more of. And here's another example kind of showcasing how valuable data really is. And so this is just a graph comparing, simple models like you have random forest, and then you have CGCNN, you have MagNet. And as you can see, as you move down and you have more data, that's really where the value of these crystal graph neural networks comes into play. Because the more data you have, you can see that there's properties and variables that the model is able to actually perform better on compared to just much simpler models. And so this is really showcasing more data does help make your predictions better, especially if you're looking at more complex models or looking at a graph-based structure to model your materials. So one way that you can kind of solve this problem is through using multi-fidelity graph networks. So if you recall, I mentioned this global state vector before, and before this global state vector was really just storing information about the system overall, so things like temperature, entropy. But what we can do instead of storing those variables is we can actually we can assign a fidelity level to all of the different functionals. So PBE being 0 here, we have HSE as 2, experimental data as 3. And then you can use the global state to actually embed this data fidelity. So you can build a model that aggregates all of the sources of data rather than having to build a separate model for each of these. And so there was a paper that did this, and they were able to see some really great results. So they saw an improvement of about 40 to 50% on those high-value functionals like HSE and experimental data when you were making predictions on band gap. So just by aggregating all of this data, they saw a significant increase in their accuracy. Another big area that a lot of you might have already thought of is, why don't we just do transfer learning? And that's a big piece, and I think that's an area that is still being explored a lot more of how can we use data from another domain that we have more of to be able to make predictions in a domain where we might not have as much data. So here's an example of doing that with formation energy, because we have a lot more data for formation energy compared to, let's say, band gaps. And so in this case, what you're doing is you're taking embedding vectors from the formation energy model that you've built, and you're putting those embedding vectors into the model for band gaps, which have much less data. And the rest of the model architecture, as you can see, is completely the same. So really, you're just reusing these embeddings into this other model. And just by doing that, you can see that the mean absolute error has decreased for the prediction for band gaps from about 0.38 electron volts to 0.32 electron volts. And this paper also found that the conversion speed was about 2 times faster through these transfer learning methods. There's also a future trend that I want to kind of highlight, which is with autonomous labs. And a big kind of bottleneck within machine learning and computational methods is really just the time that it takes to do validation. And so the thought process here is, how do we really move towards a future where we're creating this closed loop system? And this is something you've probably seen in a lot of labs, biology labs, chemistry labs. I think it's a trend that's starting to really emerge in a lot of science. And so the current kind of paradigm, let's say you're developing an organic redox flow battery, you'd oftentimes, you'd come up with a concept for a material that you want to test, you do synthesis on that material, you construct that device, and then you do a lot of testing and characterization. But this entire process can take anywhere from 3 months to a whole year. Just doing testing in itself actually can take at least 3 years. A lot of big battery manufacturers and OEMs are spending about 3 months to a whole year just testing their battery cells in lab. And this is a huge problem because you're doing testing within the entire kind of value chain of your development, right? You're doing testing within R&D to see if the materials that you're developing fit the application that you want. And then once you've even picked the material within production, you're testing for the reliability of that material. So you'll go through kind of extensive lifetime testing or degradation testing to see how long your battery will last. And this is something every manufacturer needs to actually do as part of their reliability and quality assurance to say, hey, our battery cell will last 10 years before they can really put that out there. So they have to test every single cell to be able to do this. But you can imagine it's a very, very manual process where you have technicians standing in a lab that are just charging and discharging their cells and then just measuring the degradation patterns over time to be able to say, this is the capacity and the decrease in resistance in our battery cell over time. And so that process, like I said, takes months, even years. And so there's a lot of work being done to kind of speed that process up because that's where a lot of the closed loop happens, when you're able to test your device and use that data to be able to then iterate on your concept and your materials design. And a big piece of this is also inverse design, right? Like a lot of materials research, this is really the gold star, is can we have some sort of properties that we know we want, and then get the model to give us a prediction for what structure we should use to get those properties. And so there's a lot of work being done with kind of using simulation and optimization to be able to develop a more closed loop system. For doing that, a lot of robotic synthesis as well, that is helping in that process. Now I want to end off the talk by talking about just a few opportunities. If any of you are interested in these areas, you're thinking about what are future trends. I mentioned some of the stuff with autonomous labs, but where are really the opportunities here? And some of these I highlighted during my talk as well. I think multi-fidelity and multitask ML is going to be huge for thinking about how we can integrate different sources of data into our models to be able to make predictions on areas where we might not have as much data. And I think this is really the big piece, is thinking about data and how do we really overcome that issue. And so I think transfer learning being another big area. As I mentioned, there is some work being done in this space, but I still think it's an area where there can be a lot more exploration, thinking about different ways we can formulate transfer learning methods, what types of data can we use, and how can we transfer that into new models where we might not have as much data. Another big area of research is within text mining. And so instead of collecting simulation data or experimental data, can we just use data from papers that have already been published, that already have formulations for the materials that they used and the results that they were able to discover based on those formulations. And so there is a lot of research with just using large language models to extract this information. But I think the big problem here is oftentimes papers will have a lot more of the results that worked, but they don't have as much failure modes or failure examples. And so this is something you obviously need when you're training a model. And so thinking about ways in which you can impute that data or find a way to include more examples of failure materials will be super important, especially if we're relying on text mining as a source of data. The other piece that I mentioned towards the beginning of my presentation is really combining physics and ML. So instead of having purely data-driven approaches, can we think about how we can have more intuition for physics and integrate physics into our models? And I think this is something that even on the architecture level can be explored more. There's a lot of papers that I read where I see so much data that's just not being used. And I always wonder, if we use this data, how would it change our prediction? Or if we integrated this into even the architecture and the way that we represent our models, would that really change the prediction or give us a better accuracy? So I think there's a lot more work that needs to be done in that space, especially when it comes to extrapolation. And I think that's really the big issue here. A lot of these methods that I mentioned work really well when you're interpolating and you have already a structure for the materials that you're trying to predict. But when you are trying to make predictions for materials that have not been synthesized before or they don't have a structure, it can be a lot harder to really extrapolate. And so I think having this hybrid approach is going to be really important for that extrapolation piece. The last piece I mentioned, autonomous labs. I think this is applicable to autonomous labs, but also broadly, a lot more work with inverse design. So thinking about how we can go from properties to the structure that we want, but also thinking about synthesis. This is another big piece because even after you have a prediction, you don't actually know if your material is synthesizable. And so a lot of research is being done in synthesizability, but it's oftentimes much more ambiguous. So it's a much harder field to kind of make predictions compared to, let's say, property prediction. And I think there's also a lot of work that needs to be done in closing that gap between property prediction and synthesis. Oftentimes these are separated processes, but is there a way we can have a kind of closed loop system where we're thinking about the property predictions and the synthesis with the types of models we're building? Another big piece is obviously active learning. There's a lot of work being done with this in autonomous labs, especially when you're trying to figure out even just what materials should you be testing, right? Is there a way we can rank and develop a candidate system for how we should be ranking the materials that we should be testing, and then using active learning in real time to kind of iterate based on the results that you get during your experiments. So yeah, I think those are the main areas that I would highlight. If any of you are interested, I'm definitely happy to chat more about these in detail as well. And yeah, you can also reach out to me over email, or I'm also very active on Twitter, so feel free to reach out there if you have any questions. Thank you.